Welcome to Sarasri Skill Development Programs. It gives great pleasure to Sarasri and their team to present this session on Basics of Composites Part 2. In this session, we are going to discuss the importance of ABD Matrix in composite design and analysis. This session is useful to all engineers and engineering graduates who involve in the composite design and analysis, and also engineers in the industry. Agenda of the discussion is general three-dimensional element, stress-strain relationship, anisotropic material, orthotropy and 2D orthotropic material with loading, deformation of composite laminate under load, formulation of ABD matrix, importance of ABD matrix, and its application in the industry. What is the coupling phenomena? In case of a three-dimensional theory of elasticity, we take a general three-dimensional load subjected to arbitrary loading in three-dimensional continuous body. So that induces 6 stresses components, 3 normal stresses, 3 shear stresses. Normal stresses are which are acting normal to the surface, shear stresses are which are acting in plane to the surface. So these 1, 1, 2, 2, 3, 3 are normal stresses. 1, 2, 2, 3, 3, 1 or shear stresses. If we take a stress and strain in isotropic and anisotropic material, first of all, what is the difference between isotropic and anisotropic material? Isotropic material is a material, so where the properties are constant everywhere, it is having infinite number of planes of symmetry, whereas in case of anisotropic material, it is having a distinct properties, different properties at each point in the body. In case of isotropic material which is subjected to the axial load, based on the Hooke's law, stress is proportional to strain. In other words, stress is equal to Young's modulus into strain. So whereas in case of here, strain is constant for a given load and Young's modulus is constant, obviously the stress is constant across the section in the isotropic material. Whereas in case of anisotropic material, so where strain is constant, because to maintain the equilibrium, if you apply a load on anisotropic material, so as the material is continuous, if it is subjected to the axial pull, so entire section undergoes the same deformation. So in that way, per particular reference point, there's a strain is constant. As per the Hooke's law, stress is proportional to strain. Since strain is constant but Young's modulus is variable across the section, so stress field varies in the across the section in the anisotropic material. The same is represented in the form of the pictorially. So if you take the layer of laminate with the different materials which is having a constant strain because of the loading, the same can be like extrapolated with a different stress field across the section because it is having a different Young's modulus. So behavior of isotropic and anisotropic can be described in the form of the deformations. In case of isotropic material, a component is subjected to the axial load, so it undergoes the deformation, the elongation, contraction due to Poisson's ratio. The same isotropic material is subjected to shear, undergoes shear deformation. In case of anisotropic material, it is having a different properties across each point. The same material, if it is subjected to uniform pull, so that component normal pull that can be subjected to normal strain, at the same time shear deformation or shear strain. The same anisotropic material, if it is subjected to shear loading, so it induces shear strain, but also induces normal strain. So because of the anisotropic in nature. The same, this concept can be expected to three-dimensional loading. So in case of a component subjected to three-dimensional loading, so it induces, as already discussed, 6 stress components, similarly 6 strain components. So we need to find out 6 stresses or 6 strains. So we need to have 6 into 6. We have 36 constants is required to define the either strain state or maybe stress state. So this is nothing but compliance matrix which is symmetric in nature. So these components, for example, to get the normal strain in one direction, So that will give the contribution from the stress field from the all 6 stresses. So that's correspondingly S11 into sigma 11, and it will go up to S16 into tau 12. But same three-dimensional loading can be brought into two-dimensional loading. So in case of a plane stress problem, so all this out of plane stress components become zero. So then this reduces only these components and these components. All this will become zero if it is subjected to two-dimensional plane stress. But even sigma 33 also exists because of the Poisson's ratio. Same stress strain relationship for three-dimensional orthotropic component if it is subjected. First of all, what is meant by orthotropic material? So orthotropic material is having three mutually perpendicular planes of elastic symmetry in each point. So that means if this is the orthotropic ply, best example orthotropic is like a wood. But in case of our discussion, a composite lamina which is having fibers oriented in like material one direction, so that can be treated as a orthotropic ply. Or it is also a special orthotropic material where it is a transversely isotropic material, where in case of like a fiber direction it is having a distinct property, but in case of transverse to the fiber direction it is having a isotropic behavior, because the properties in the transverse plane and perpendicular to transverse plane, so both will be equal. So that transversely isotropic or special orthotropic material can be taken here for reference. So that can be studied for the using the plane stress approach. So same this two-dimensional like approach, we can see that one in case of anisotropic material, these are all the elastic constants required to define a strain field or a stress field. So same if in case of orthotropic material, so these components will become zero, because in case of orthotropic material, so extension shear the coupling won't happen, and so that's the reason these components become zero. So only these four components exist: S11, S22, S66, and S12. So why this is this behavior is, in case of orthotropic material, if a component is subjected to like a normal load, it only produces normal strain. But if it produces a shear load, it produces only shear strain. So that's the reason these components become zero. For example, to get a normal strain, so the contribution from these normal stresses will contribute, and shear stress won't contribute for that. These flexibility components are dependent upon the Young's modulus. Similarly, stress strain relation for 2D orthotropic material. So far we have discussed 2D orthotropic material, which has been mathematically defined. Now it can apply the practically. If a component of 2D orthotropic material is subjected to tensile loading in the uniaxial direction, so what kind of stress field it will experience, what kind of a strain field it will experience, we will discuss. So based on the orthotropic material nature, it is a plane stress problem. So in case of plane stress, that out of plane stresses won't be there, and hence these components induces, because of the normal loading, it induces only normal strain. So that is sigma 1 is equal to S11 into P, as already discussed from this like flexibility matrix. So in case of orthotropic material, as it doesn't induce, if it is subjected to normal load, it doesn't induce a shear strain. So that's why these components become zero, and even though it produces a normal loads, the shear strain won't be there in this component. Similarly, if it is subjected to shear loading, so what kind of like behavior it behaves? So because of shear loading, so this will induce only like a shear strain, doesn't induce any normal strain, because these components become zero in the flexibility matrix. So far we have discussed about composite lamina, and now the same lamina can be stacked one over the other to form a composite laminate. If this laminate of a thickness T, which is consist of n number of flies, so when subjected to the axial load, so what is this behavior and how it will behave will be discussed now. So in case of this before loading, this it is having a middle plane, it is almost like a straight line. So after the loading, subjected to the uniform tensile loading of this thickness T laminate, so because of this layup configuration, it can bend its middle axis, and because of this normal like a tensile load, so that induces a different kind of strains. So the total strain experienced by this loaded body is like a function of the mid-plane strains plus the contribution from the away from the like a middle layer at a particular distance. What is its contribution due to curvature? So in the matrix form, so this normal strain in the total strain in xy component is expressed as so mid-plane strain at middle plane and contribution from this curvatures. So in other words, total stress field is a function of this Q matrix and mid-plane strain and curvatures. So in case of like a forces are acting on the laminate, so that can gives rise to stress field. So this is obtained through this relationship. So finally this can be formulated to A matrix, which is a function of Q matrix and its distance from the mid layer to the particular location of the interest. In case of a B matrix, so this is also a function of the Q matrix and the distance from the mid layer to location of the interest. It is like a square term. This is like a linear and this is like some kind of curvature in the effect, higher order term. So in case of out of plane, so total moments equal to stress field through this relationship. So that can be formed. Total moment is equal to like function of these mid plane strains plus the curvature. So instead of in the previous like a force, we have here A and B matrix, but here we have B and D matrix. So in a nutshell, total forces and moments can be written as a like a matrix into like strains and curvature. So this matrix is known as laminate stiffness matrix, or simply it is known as ABD matrix. So that can be expanded into in XY terms. So this is like A matrix, B matrix, and D matrix. So for example, given force field, to get the what is its contribution from the strains and its curvature, so function of this matrix. In case of moments, so it is like a function of the mid-plane strains and curvatures, but here the components is B matrix and here it is a flexural matrix. So totally it is NM is equal to ABD matrix into that strains and curvatures. So this A matrix relates to forces to strains, D matrix relates to moments to curvatures, B matrix relates to forces to curvature and moments to strains. So this is A matrix is a membrane stiffness matrix. So D matrix is a flexural stiffness matrix, and B matrix is a coupling stiffness matrix. So far we have discussed so these terminologies. There are different kind of laminates: symmetric laminate and balanced laminate. Symmetric laminate is a laminate where if you are positioning a layer with a particular angle at a distance from the middle axis, same like a layer can be placed below the middle axis at a same distance, so that will form the symmetric laminate. In case of a balanced laminate, so this is slightly different as compared to symmetric laminate, but in case of a balanced laminate, if we are placing a particular angle like a layup at a particular distance, it need not be like opposite angle, need not be at the same distance from other side. It can be anywhere outside the mid layer, so that will form like balanced laminate. So because this symmetric and balanced laminates are very much important, so this can create like a comfortable position while solving the design and analysis, because placing the laminate as a symmetric, it eliminates some of the terms, so that is easy to analyze. So finally, that ABD matrix can be formed in form of what actually is it will be discussed. So this is forces and moments. It is like A matrix and B matrix, and it is like a function of the strains and curvatures. So these terms are important. These A1, A2 represents the extension, like a plane stiffness, extension stiffness, and this A16, A26 are extension and shear like a terminology like stiffness. So whereas this kind of B16 to D26 corresponds to this is coupling phenomena. So that involves this D matrix is like a flexural stiffness matrix. D16, D26 relates to bending moment to twist like a contribution. because if you are having symmetric and balanced laminate, some of these terms will go at zero. So that we will discuss in the subsequent slides. So if you take a total, this is like a laminate with different like principal material directions. So that is subjected to a force field Nx, Ny, Nxy, and the same it can be like transformed into stress field like sigma 1, sigma 2, sigma 3 in fiber directions, like material principal material directions, and like transverse direction and through thickness direction. Similarly, shear stress field, so that is acting like tau 1 2 corresponds to in the 1 2 plane, corresponding complementary shear sigma 2 1. So this tau 1 2 is equal to tau 2 1. So that's why total 6 stress components are involved in any like three-dimensional loading. So let us take that laminate with is loaded with forces and moments. We can take a general standard laminate like 0 degrees, 90 degrees, plus minus 45, and that can be arranged in a particular fashion. So that give like whether symmetric laminate or anti-symmetric or balanced laminate or quasi-static laminate. So that can be seen based on the layer configuration. So these four plies can be arranged in to start with 0 degrees, 90 degrees, 45, minus 45, and exactly the same it can be mirrored this side. So that forms exactly the whatever this is the middle plane. So whatever it is having in above plane, exactly the replica is having below middle plane. So this forms the like symmetric laminate. So the layers of the same material thickness at a different locations having a same theta. So because of the advantage of symmetric laminate is the coupling matrix will get vanished. So there is no in plane and out of plane like a coupling in case of a symmetric ply. In case of balanced laminate, there are two types of balanced laminate. Balanced laminate with 0 and 90 degrees, balanced laminate 0, 90 and plus 45 and minus 45. So in case of a cross ply laminate with balanced, so where the terms like extension shear terms will go vanish in this case. In case of a cross ply laminate, balanced laminate, in case of a like balanced laminate with 0, 90 plus minus 45, so A126 and A26 will become 0. So you can see here this is like symmetric laminate, but at the same time it is a balanced laminate. So wherever we have the 0, there will be corresponding opposite like a 90. So there is a plus 45, there is a minus 45, there is a minus 45 corresponding plus 45. In case of balanced laminate, we need not maintain exactly the same distance whichever a particular layer is from the middle layer. So only the like positive and negative like a layer configuration is important. In case of a balanced laminate, there is no in-plane direct and shear coupling exists because of this. If you are putting a positive theta and negative theta, automatically that like direct and shear like a coupling will get eliminated. So illustration of coupling phenomena in ABD matrix. So this is like force is equal to forces and moments equal to ABD matrix times like a strains and curvatures. So these terms represent to like extension shear. These terms represent to shear and coupling. So these terms represents to bending and twist like a contribution. So this B matrix represents like it is a coupling between this flexural and like a plane like axial like a stiffness. So illustration of coupling in a more detailed manner. So if we already discussed this cross ply laminate which is having 0, 90, 90, 0. So this is a cross ply laminate, but it is also a symmetry laminate. So this is and it is a balanced laminate. So A16, A26 is 0, B matrix is 0, and D16, D26 also 0. But in case of a balanced and symmetric laminate, so we have A16 is equal to A26 is equal to 0, and at the same time B matrix is 0, because here this is a symmetry and it is balanced with of 0, 90 and 0 plus theta and 90. So in case of a balanced laminate, this A16 and A26 are 0. So where exactly we have theta and minus theta. So but it is not a symmetry laminate. So in case of a symmetry laminate, where exactly the whatever theta is above the middle plane, the same theta can exist below middle plane of the laminate. So that's why it is this B matrix is 0, but here it is there is nothing, like it is not a balance. So A16, A26, D16, D26 not become 0 here. In case of a quasi-isotropic, where exactly we can put equal number of places of 0, 90, 45. So this will form quasi-isotropic. So based on this quasi-isotropic, it behaves like isotropic nature. So that means it is having uniform properties in almost every direction. So anti-symmetric laminate, it is is opposite to symmetry. So whatever the configuration plus theta minus theta we take, exactly it will be opposite like other side of the mid plane. So because of the anti-symmetric laminates, we have this A16, A26 becomes 0 and D16, D26 becomes 0, but B matrix is not 0, so it is not easy to analyze because it introduces the additional stresses because of this coupling. Quasi-isotropic, as discussed, is almost equal like behave like isotropic plates. It is independent of orientation. So this ABD matrix is important because because of the ABD matrix we can identify the fiber like a ply stresses. So what kind of ply stresses it will experience based on whether it is a tension or a shear, and based on that we can say that failure mode of that particular ply in the like layup configuration, ply failure and failure index, and so that can be classified as a failure mode, whether it's a tension failure mode or compression or shear and through thickness. So that's why ABD matrix is very important composite design analysis. ABD matrix stiffness, laminate stiffness matrix. The way the layup is like configured, so a particular type of behavior can exist in the laminate a design, so that the loading also can take place accordingly based on the like laminate stiffness. So far we have discussed all aspects of the ABD matrix. Let us take a practical example of this ABD matrix, how it behaves in case of with a practical scenario. So given configuration, so in case of ABD matrix, so let us take a glass a material with these properties like ply properties. So that can be placed accordingly. Let us take starting from the layer on top. You can say like 0.1 is the thickness and 0 is the angle, and you can say second is same glass. We can repeat. We can take a single material and this is a 90 degrees. This plus 45. This is minus 45. So we take a 4 layers of the 0, 90 plus 45 minus 45. That is mirror this about the middle layer, and we get the almost like exactly the symmetry of the above 4 layers, 4 plies. So this forms like a symmetry laminate. So as per our discussion, the symmetry laminate can induce like a B matrix has to be 0. But this matrix, whatever it has been, the 8 plies, this is also balanced laminate, because for 0 degrees there is 90 degrees, for 90 degrees there is a 0 degrees opposite side, for plus 45 there is a minus 45, for minus 45 plus 45. So this is also balanced. So this is a symmetry and balanced laminate. So as per the discussion, so this B matrix and A16 and A26 terms has to be 0, and D16 and D26 terms need not to be 0. Let us see how whether it comes from the analysis of this laminate. So here we can see that this is A matrix and this is a D matrix and this is B matrix. Since it is a balanced laminate, so A16 and A26 are 0, and since it is a symmetry matrix, B matrix is 0. So this is a balanced laminate with 0, 90, plus minus 45. So these terms are not 0. This is already agreed with our earlier discussion. So now, so this matrix is stiffness matrix, and this is like a flexibility matrix. This is inversion of the ABD matrix. So that will be useful. So whether we can give the like force field, with this one we can find out the strain field, or we can have this flexibility inverse matrix. By giving the forces you can get the strains. So either way we can do. So if you see this one same, we can alter this, we can define a matrix in a other way. So let us take, it is not a symmetry, so it is like a different kind of matrix. Let us see how it behaves. By introducing some different layer at a like layer, so it spoils the entire symmetry and balance in nature. So then let us see how it behaves. So it see none of the terms are 0. So it is A matrix is not 0, D matrix is not 0, B matrix is not 0. So just by introduction of the one layer of a different configuration. That's why this layer configuration is very much important. So to get the like a prescribed properties of the laminate stiffness. So based on that, our analysis will be easy. So if it is a like a coupling matrix, it induces unnecessarily like additional stress field. So let us take not only this, we can take a anti-symmetric laminate. So whatever this laminate we have, we can take a different configuration. So anti-symmetry, that nature is whatever we define above the midplane, there should be opposite layup configuration below midplane. So that becomes like an anti-symmetry. So this is anti-symmetry. This is not a balance. This is not a like symmetry. So then we can see how exactly for so 90 there won't be any 0, plus 45 there is a minus 45. This is anti-symmetry. So how exactly it behave, we can see this from the analysis of the laminate. So we can see here, so this is like anti-symmetry. So these A16, A26 are 0, and D16, D26 are 0. So you can see B matrix is not 0. So this is what, as we discussed earlier, this anti-symmetric, it is not a symmetric, so it introduces an additional stress field in this one. And also this through ABD matrix, through layup configuration, we can like determine at what location what layer can be placed. Suppose extreme like outer fiber, in case of a component is subjected to bending load. So plus like outer layer and bottommost layer can be having a particular choice. Let us take 0 or 90 degrees. So that based upon the that bending load, so that introduce. But whereas in the middle layer we can take like plus minus 45, where if it is a transverse shear like a loads are higher. So accordingly we can control this layer, and at the same time maintain symmetry and balance, so that it is easy to like a load path, it is clear and it is easy to analyze this component, that because that won't introduce any additional stress field. So in a nutshell, so this is the like discussion about ABD matrix, so which is very much important in the composite design and analysis. So generally whenever we are defining, we are approaching to get a solution for a given a project or for a given a like problem or a challenge. So to get the best solution, we always use the process, our skills properly, our ideas properly, and in addition, so the relevant to like right framework to that particular project can be used to get the best solution. So in other words, solutions at applying rational thought, skills and relevant to the industry, the right framework to the industry. So shortly named as a Sarasri. Thank you. If the content of this like webinar is useful, subscribe the Sarasri channel. If the more details are needed for discussion, so contact sarasri.etechnology@gmail.com. So in some more sessions will be like uploaded in near future. Thank you.